This quiz is all about Lewis structures and some of the finer points in drawing Lewis structures, such as resonance and formal charge. So in our first example, we have two molecules, C2H4, C2H6, and we want to propose Lewis diagrams for these two compounds. And as we're looking at the first one, C2H4, this is the best Lewis structure. Remember that in their most popular, not popular necessarily, but their most stable, I guess, state, their most common state, carbon likes to make 4 bonds with no lone pairs. Hydrogen likes to make 1 bond and then no lone pairs for it either. Therefore, if we put the 2 carbons together in the middle and we put some hydrogens around them, we're going to see that we need a 4th bond to link between the 2 carbons. This will only have 3 bonds each. This uses up the right number of electrons. There's 4 on each carbon plus 1 on each hydrogen. 12 total, and we have 6 bonded pairs of electrons here, which is our 12 electrons. Octets are fulfilled, and this is a good Lewis structure. What about C2H6? Well, it looks pretty similar, but it looks like this now. This is ethane, C2H4 is ethene, and now we have all of the electrons that are placed, where it is 14 electrons, and they're all placed here. Both carbons are filled with hydrogens. They have 1 bond to each other and then 3 more to fulfill the 4 bonds carbon likes to have. And here we are. Just as a note, this is getting into organic chemistry a little bit, where we have ethane, that means no double bonds, and ethene, meaning a double bond between the carbons. And notice that when we make this double bond, we have 1 less hydrogen on each carbon. We would call ethene an unsaturated hydrocarbon and ethane a saturated hydrocarbon, with that degree of saturation being, is it full of hydrogens or not? Like a sponge is saturated, so too can carbons be saturated if the maximum number of hydrogens are around them. That's true for the ethane, not for the ethene. Okay, the next one says, what about the carbon-carbon bonds on each of these 2 structures? We want to say which one has a greater bond energy, which is to say a stronger carbon-carbon bond. And the answer here is it's going to be based on the order of the bond. Higher order, meaning more bonds, meaning double bond is higher than single bond, is going to be a higher bond energy. And therefore, ethene is going to have the greater carbon-carbon bond energy. It shares more electron pairs, it makes a shorter bond, and therefore is going to have a stronger bond. All right, the next part is talking about resonance structures. So we have 2 resonance structures for nitrate, and we want to label all atoms with their formal charge, and then, based on that formal charge, decide which is the better major resonance structure with a little explanation. So recall that as we're dealing with formal charge, the formal charge calculation is the number of valence electrons an atom arrives with, minus the lone pair electrons, minus half of the bonded electrons. Remember, each single bond contains 2 electrons, and therefore saying half of the bonded electrons is like attributing 1 of each of those electrons to each atom that's engaging in that bond. If we do such a thing, we get the following formal charges on the left nitrate: +1 for the nitrogen, -1 for the single bonded oxygens, and 0 for the double bonded. And if we want to see how we calculate that, for the nitrogen, it's 5 valence electrons nitrogen arrives with, no lone pair electrons on the nitrogen, and it's got 8 bonded electrons based on the fact that it has 2 single bonds and 1 double bond for 8 electrons that are engaged in bonding with that nitrogen. This gives us a +1 formal charge for nitrogen. The oxygen on the left bottom is going to have 0 formal charge based on the 6 valence electrons it starts with, minus the 4 lone pair electrons it still has, and then 1/2 of the 4 bonded electrons that are bonding with the oxygen. And the top and right oxygens are going to have a -1 formal charge that's calculated very similarly to how we talked about before. And these are the formal charges on the left nitrate. On the right nitrate, we get these formal charges, and here the nitrogen is going to be 5 valence electrons minus no lone pairs, minus 1/2 of 6 bonded electrons, and this is going to give us +2. Excuse the typo there, that should be a 1/2 of 6 bonded electrons. And for the oxygen, this is going to be the 6 valence electrons minus 6 lone pair minus 1/2 of the 2 bonded electrons, just 1 bond for each of those, which gives us -1. And therefore, we decide that the left nitrate is the preferred resonance structure, and this is because it's minimized its formal charge better. It does have negative formal charges, but these are put on the oxygen. It's got alternating formal charges, which is desirable, but the big thing is just that the size of the magnitude of the formal charges is smaller on this structure than the right structure. Not to mention, the right structure also doesn't have filled octets for that nitrogen, but we can still assess a formal charge structure and whether it's a good resonance structure, even if our octets aren't fulfilled, but that is also a really good reason why we want to choose the left. Finally, we want to say, well, if that left structure is the one we want, does it have any equivalent major resonance structures? And we want to show which ones they are, including the one that we chose in the previous question. And here they are. These are the 3 resonance structures for nitrate. Note that that double bond is not fixed in any one location, but is actually spread across all 3 nitrogen-oxygen bonds. This is critical to understanding resonance. These are all 3 equivalent major resonance structures, and this means that nitrate is all 3 of these at once. It has 1/3 the character of each of these 3 structures, and that would be nitrate's true structure. It's no one of these, it's all 3 at the same time with equivalent parts of each, as they are all equivalent resonance structures. And the final question is going to continue to build on this. We want to know what the bond order of the NO bonds in nitrate are. Remember that if we had a double bond, we would call it bond order 2, single bond order 1. And here, note that every nitrogen-oxygen bond has an initial bond, it's single bond, but then there's this double bond that's spread over all 3 bonds. This increases the bond order of each nitrogen-oxygen bond by 1/3, and therefore it's going to be bond order of 1 1/3. We can draw the resonance hybrid for nitrogen something like this, where we show that nitrogen keeps its positive formal charge, and this notation shows that there is a partial negative charge that's equivalent on each of the oxygens, and that extra bond is spread across all 3 nitrogen-oxygen bonds.